Hello everyone, how are we all doing today? Last time out we discussed about Picard's iteration method where we took two extra examples in addition to the ones we already took in the first video. So in continuation of our ordinary differential equation series, we are going to be talking about differential equations solvable by variable separation today. So a differential equation is said to be solvable using this method if it is of the form f of y with respect to y is equal to g of x multiplied by the differential of x. That is, consider on the left-hand side, we are having a function in y only and also a derivative in y only. So everything on the left-hand side is directly related to y, while everything on the right-hand side has to do with functions in x, that is, g as a function in x and the derivative of x. So to obtain this solution, we can just integrate both sides and we are going to get our answer. It's a very straightforward procedure. And here we have our working rule for this method. So the first thing we have to do when given differential equations of this form, when given differential equations is we have to separate the variables in this form f of y multiplied by the derivative of y is equal to g of x multiplied by the derivative of x. After that, we integrate both sides and we have the integral of f of y with respect to y is equal to the integral of g of x with respect to x. Then on doing that, we add an arbitrary constant to the right-hand side of the obtained equation. So let's take an example to show us how this method works. Or more like examples actually. So in this example, we ask to obtain the solution of the differential equation dy dx is equal to x into bracket 2 ln x plus 1 divided by sine y plus cos y. So this is very straightforward because we can all see that the differential equation, all we need to do is we cross multiply, then we have the functions in y on one side, the left hand side, and the function in x on the right hand side. So let's do that. So on cross multiplication, we have dy into bracket sine y plus cos y will be equal to dx into bracket x into bracket 2 ln x plus 1. So we can rearrange this as sine y plus cos y into bracket dy will be equal to x into bracket 2 ln x plus 1 dx. So we've done the first step of the working rule. So we move on to the second step, which is to integrate both sides. So we now integrate both sides, sine y plus cos y with respect to y will be equal to the integral of x into bracket 2 ln x plus 1 with respect to x. So we can further expand this to give us integral of sine y dy plus the integral of cos y dy will be equal to the integral of 2x ln x dx plus the integral of x with respect to x. So we can now do this. The integral of sine y with respect to y is going to give us minus cos y plus, when we integrate cos y with respect to y, we're going to be having sine y, and that's going to be giving us 2 integral of x ln x plus, sorry, with respect to x plus x squared divided by 2. So the integral of x ln x cannot be easily evaluated like the others. So we are going to use integration by parts. So let's single that out. So integral of x ln x with respect to x. Remember that our integration by parts states that integral of u dv is equal to uv minus the integral of v du. So on evaluating this, for x ln x, integral of x ln x. So we're going to select our u as ln x and our dv, sorry, and our dv as x dx. So our du dx now becomes 1 over x, and hence our du will be equal to dx divided by x. Our dv is equal to x dx. So our v now becomes the integral of x dx, which is equal to x squared divided by 2. So applying our formula, integral of u dv is equal to uv minus integral of v du. We now have the integral of x ln x dx will be equal to uv, which is x squared divided by 2 ln x, minus the integral of v du, x squared divided by 2 multiplied by dx divided by x. So we have our integral of x ln x dx now to be equal to x squared all over 2 ln x minus the integral of x all over 2 dx. So we have our integral of x ln x dx to be equal to x squared over 2 ln x minus x squared divided by 4. So 2 integral of x ln x dx now gives us 2 into brackets x squared over 2 ln x minus x squared divided by 4. So we have our 2 integral of x ln x dx, sorry, will be equal to x squared ln x minus x squared divided by 2. So we now have to substitute this into our original integral that we obtained. We have minus cos y plus sine y is equal to 2 integral of x ln x dx plus x squared all over 2. So this becomes minus cos y plus sine y is equal to x squared ln x minus x squared over 2 plus x squared all over 2. So this becomes minus cos y plus sine y is equal to x squared ln x. So in evaluating this, we've done the working rule too. We now evaluate the working rule 3, which says that we just add an arbitrary constant to the right hand side. So writing the left hand side as sine y minus cos y will be equal to x squared ln x plus c. And this gives us the general solution of the differential equation x into bracket 2 ln x plus 1 divided by sine y plus cos y is equal to dy dx. So let's take a second example. So we have to solve this differential equation cos x plus y dy is equal to dx. So in order to solve this, it's not something that we can solve. It's not an equation that we can solve in a very straightforward manner as the first example we did. So to make our work easier, we make x plus y equal to an arbitrary letter, say p. So let's x plus y be equal to p. So we can differentiate this implicitly to obtain the value of dp dx. So dp dx now becomes, when we differentiate x with respect to x, we have 1. But when we differentiate y with respect to x, we have dy dx. So on making dy dx separate the formula, we have dy dx is equal to dp dx minus 1. So now we have our dy dx to be equal to dp dx minus 1. Now from our original differential equation, we have cos p dy is equal to dx. So we can write this as dy dx is equal to 1 divided by cos p, and this gives us sec p. So we now substitute the value of dy dx that we obtained from this equation above. We have dp dx minus 1 to be equal to sec p. On taking 1 to the other side, we have dp dx to be equal to sec p plus 1. Now we can simplify this to give dp dx is equal to 1 divided by cos p plus 1. And on taking the LCM, we have cos p bracket 1 plus cos p. So our dp dx is now equal to 1 plus cos p divided by cos p. Now this looks like an equation that we can solve using the separation of variables method. So bringing all the functions in p to the left side and the functions in x to the right side. By cross multiplication, we have cos p divided by 1 plus cos p dp is equal to dx. So we've satisfied the working rule 1. What we have to do now is the working rule 2, which is to integrate both sides. So in integrating both sides, we have integral of cos p divided by 1 plus cos p dp is equal to integral of dx. So now we are going to do a bit of manipulation just to make our our integral, just to make our integral simpler. So we have integral of cos p divided by 1 plus cos p with respect to p is equal to integral of dx. We can rewrite the numerator of the left-hand side as the integral of cos p plus 1 minus 1 divided by 1 plus cos p dp is equal to, let's evaluate the integral on the right-hand side. When we integrate 1 with respect to x, we have x. Then let's just add our arbitrary constant c. So that's working rule 3. So this becomes integral of cos p plus 1 divided by cos p plus 1 minus 1 divided by cos p plus 1 dp is equal to x plus c. So we have integral of 1 minus 1 divided by cos p plus 1 with respect to p will be equal to x plus c, which is our arbitrary constant. So this becomes integral of dp minus integral of 1 divided by cos p plus 1 dp is equal to x plus c. So on the left-hand side, we can evaluate this first integral easily, just as we did for the right-hand side of the equation. But the second integral is what we now need to focus on. So let's name this equation asterisk so we can refer to it much later on. So let's evaluate the integral of 1 divided by cos p plus 1 dp. So cos p from our trigonometric ratio can be written as cos p over 2 plus p over 2. So using our trigonometric ratio, we know that cos a plus b will be equal to cos a cos b minus sin a sin b. So we are going to be applying this, and we will write our cos p as cos p over 2 cos p over 2 minus sin p over 2 sin p over 2. So our cos p now becomes cos squared p over 2 minus sine squared p over 2. So we can substitute this in our integral. So we have integral of the p divided by cos p plus 1 is equal to the integral of the p divided by cos squared p over 2 minus sine squared p over 2 plus 1. Also recall that 1 minus sine squared theta is going to be equal to cos squared theta. So therefore, 1 minus sine squared p over 2 from the denominator will be equal to cos squared p over 2. So we can substitute it here. We have integral of the p divided by cos squared p over 2, cos squared p over 2 plus cos squared p over 2. So this becomes integral of the p divided by 2 cos squared p over 2. And this looks easier to simplify. Can I write it as 1 over 2 integral of 1 divided by cos squared p over 2 dp. So we know that 1 over cos squared theta is going to give us sec squared theta. And we write it as 1 over 2 integral of sec squared p all over 2 dp. When we integrate sec squared theta, we have our result as tan theta. So this becomes 1 over 2 tan p all over 2. So we've evaluated the second integral. We now have to substitute back into equation asterisk. From equation asterisk, we have integral of dp minus integral of 1 divided by cos p plus 1 dp is equal to x plus c. So on evaluating this, we have p minus 1 over 2 and p over 2 will be equal to x plus c. So the last part of this is to substitute our values of x and y for p. So we can recall that x plus y is equal to p. So we can substitute it back into the original equation. We have p minus 1 over 2 tan p over 2 is equal to x plus c. Therefore, we have x plus y minus 1 over 2 tan x plus y divided by 2 is equal to x plus c. So on collecting like terms, we have x on both sides, so they cancel out. I have our y minus 1 over 2 tan x plus y divided by 2 is equal to c. You can take the tan x plus y over 2 to the other side, and we have y is equal to 1 over 2 tan x plus y divided by 2 plus c. And this is our solution for the differential equation cos x plus y dy is equal to dx. So to solve this differential equation, it's also very straightforward. You can see that we have a combination of functions in y and x. So to start with the solution, let's put them on opposite sides. So we have sec squared x tan y dx is equal to minus sec squared y tan x dy. So dividing both sides by tan x tan y, we're going to be having sec squared x tan y divided by tan x tan y dx to be equal to minus sec squared y tan x dy divided by tan x tan y. So this simplifies to give us sec squared x divided by tan x dx is equal to minus sec squared y divided by tan y dy. And we've successfully separated the variables. So we have the working rule 2, which is to integrate both sides. Integral of sec squared x divided by tan x dx is equal to minus integral of sec squared y divided by tan y dy. This is our integral. So to evaluate both integrals, we can use the u substitution method. So for the left hand side, we can let u be equal to tan x. So our du dx is equal to sec squared x. And making the x the subject of formula, we have the x is equal to the u divided by sec squared x for the left hand side. And for our right hand side, can let tan y be equal to v, and the v dy will be equal to sec squared y. Making the y the subject of formula, we have dy is equal to dv divided by sec squared y. So you can substitute this to both sides of the equation. So we have integral of sec squared x divided by u multiplied by du divided by sec squared x will be equal to the minus integral of sec squared y divided by v multiplied by dv divided by sec squared y. So cutting out the fractions, sec squared x to cancel sec squared x in the numerator and denominator for the left hand side, and sec squared y cancels sec squared y for the right hand side. So we have integral of du divided by u is equal to minus integral of dv divided by v. So we have ln u on integrating is equal to minus ln v plus c. Let's use small letter c. We'll see why we're using small letter c at the end of the problem. So we have ln u plus ln v is equal to c. And recall that if we have ln a plus ln b, we can rewrite it as ln ab. So using that, our ln u plus ln v is equal to c. We have ln uv to be equal to c. Now we recall that u is equal to tan x and v is equal to tan y. So we have ln tan x tan y is equal to c. We can leave our answer this way, but we can further simplify it, which is the best option. So we have, recall that when we have ln a to be equal to b, we can write a as e raised to power b. So we are going to apply this principle here, and we will write our result as tan x tan y be equal to e raised to power small letter c. And since e is a constant, And also our small letter c is also an arbitrary constant. We can now rewrite our solution as tan x tan y is equal to the big C, which we have been adding to both sides. And this is our solution to the differential equation sec squared x tan y dx plus sec squared y tan x dy is equal to 0. So the method of solving differential equations using variable separation is a very straightforward method. As long as we are able to separate the variables into two parts, one with the independent variable on one side, then functions concerning the dependent variable on the other side. From there, we get to integrate both sides to obtain the solution. Then we add an arbitrary constant to the right-hand side. With this, we've come to the end of this video on differential equations solvable by variable separation. In our next video, we are going to be looking at homogeneous differential equations. So to see how we are going to solve homogeneous differential equations, how we can test for homogeneity and the likes. Thank you very much for watching this video.